Okay, so we're moving on with our conceptual stuff, and since I switched to my laptop built-in microphone, like I told, I'm going to stay a little bit less animated, which may make class a little bit more boring, but that's just today, hopefully. Anyway, so here's a view of memory as numbered boxes. You know, when you talk about computer memory, it's probably all about some kind of circuitry and chips and hardware and different kind of connection buses inside the computer with, like, you know, electrons moving along the wires and everything. But we don't want to look at that level. We don't want to bother ourselves with looking at some kind of low level. We really just say, what would be the most helpful view of computer memory for a programmer who wants to be productive and effective? And guess what? I don't think this can possibly ever be simplified more than what you're looking at. You're looking at the row of boxes. You can have like 4 or 8 gigabytes of individual little, you know, cells that can remember binary numbers, okay? And each cell, guess what, gets perfectly uniform sequential numbers. And the first number is 0, which we refer to as zero-based numbering or sequencing, okay? Simply because, you know, it's for multiple reasons. Using 0 as a base number is very convenient, right? What 0 really means in 0 numbering as opposed to 1, 2, 3, 4, 5, a 1 base numbering, is that 0 says that to get to this location right here, location 0, you have to take 0 steps away from the beginning of your memory array. So that's why. So it's like, typically memory is like, okay, how far is this location? Oh, it's like 4 spots away from the beginning. Look, 1, 2, 3, 4, exactly. That's location number 4. Whereas 0, how far away is location 0 from the beginning of memory? Well, 0 steps away. So basically, you don't have to make any steps away from the beginning to find location 0. So that's the idea of 0. And it has very convenient arithmetic you know, implications in when you try to calculate where things are or how things are aligned or even measure distance in memory between different things. It's just like zero-based approach to number locations in memory is very, very effective. Just remember, Java does that, C does that, C++ does this, and a whole bunch of other programming languages do this as well for just like a default normal numbering of sequences of things. And of course, memory is a sequence of boxes. Okay, and so they could be called placeholders or boxes that basically have numbers. So they're all numbered. Okay, so each memory location can be accessed at the same speed. So we call it random access memory. So if this was like a tape recorder, right? For the tape recorder, it would take some time to fast forward or backward to find particular piece of information. Here, any location, you know, whether it's like 2 million bytes from the beginning of memory or 20 bytes from the beginning of memory, doesn't matter. It's the same speed. Okay, so it's just this is completely random and accessible to us. So we already mentioned it's sequentially numbered starting with 0, okay? And the number corresponding to a given spot is called the address, okay? So we're going to stick with some official terminology here, obviously. We have to, right? We have no choice, but we could use numbers, but we're going to basically try to be somewhat disciplined and follow the terminology that most people would use when describing things. And so we say memory, computer memory, or random memory that we're going to be using as a model for what our programs do and can have available to them. So those numbers are addresses. And by the way, there is nothing. This picture here is absolutely great because it really never gets more complicated than this. And yet people find ways to confuse themselves with the concepts of computer memory. This is the picture that I want you to have for as long as we use the same kind of programming languages. This picture of computer memory and the way things stored in computer memory is going to be the same in C and C++ and Java. It's just the same. It's just this numbered sequence. Okay. So we already mentioned curly braces, and just wanted to highlight here separately that curly braces do manage computer memory. In other words, when you use your braces, somehow computer begins to say, oh, within those braces, there's stuff in these braces. For example, there could be variables declared or created between those curly braces, and those variables have certain visibility in the program. Some parts of the program won't be able to access them. Some other parts of the program will perfectly be able to access them. Therefore, it's going to essentially place it in some area of memory and remember that specific area of memory. So that's one of the roles of braces. Like I told you, it's like a fence, pieces of fence that you can use to group things together or put them in the same scope. That would be more general and more accurate technical term. Okay, so curly braces definitely manage program memory, and interestingly, and let me just maybe do a bit of a drawing here to demonstrate. Okay, so I'm about to erase this pretty picture. So right here, when we say something like, I don't know, we have this, we can have this int main, okay, and in C main doesn't take any parameters. We use curly braces right here, okay, and we can say integer x equals 1 to 3, okay, and then we can say print f, which stands for formatted print. That's why you have to provide like format string for your output. It goes with %d like this, and you say comma and x, and this supposedly will print 1 to 3 on your computer screen. Okay, and you also need to include stdio, a header. I'm not going to put this on this picture, but I'd like to tell you that this variable x, okay, so if I actually resize this, oops, if I just resize this a little bit like this, doesn't want to go this way, so I'll go this way. All right, so basically what's going to happen, that if we have this memory array, right, someplace we're going to place this variable x with its own value 123, okay, and someplace else, interestingly, there will be in fact inside the text memory segment, there will be pieces of executable program. So whatever happens between those curly braces, printf contributes executable code, and declaration of variable x contributes to computer memory, the creation of a variable in memory. Okay, so clearly whatever happens between those curly braces can give you two kinds of information in computer memory. The data, such as this variable x, which is just named memory location, we gave it name x, and also printf, formatted printout, probably will create a whole bunch of computer instructions which will somehow find a way to print variable X on your screen. Okay, so that requires some code, and that code obviously is going to be located. I'm trying to find my mouse here on the screen right here, because this dot is so small I can barely see it here. But nevertheless, to find where I am on the screen. Okay, so this portion here will say executable code, and this portion here will say is the some data. Okay, so whatever happens inside your curly braces can be or usually is contributing both. Yes, question.
What is the %d?
Oh, I will talk about it in a few seconds. This basically says print decimal value. That's what it is. And I can see that you're taking notes, and that makes me feel very good, because usually when I take a class, the only thing I can possibly retain from any class I take is notes. Okay, seriously. Like there's some interesting classes I took, like maybe, you know, as my professional career development, maybe like 3 years ago, 8 years ago, 10 years ago, and guess what? I still have my notes, and they're the best way to remind me of what was happening in those classes. I cannot, without it, I cannot really remember anything. Okay, so so this is what it says on this slide, that between your curly braces, what happens is that local variables can be created in memory, and also executable statements will also be written down, and they will be loaded into computer memory, and they will be working with your data. Okay, what is executable instruction? So again, I guess we're just going over some very, very basic terminology here. Okay, so we say that the running program means executing a series of CPU commands. Okay, and often it happens in a loop. So computers really repeat the same things really like millions of times. For instance, when you're typing on your keyboard, what happens? A signal comes in, some kind of interrupt flag is set, your CPU you know, goes to retrieve the code that comes from the keyboard, places it in some buffer. The next key is pressed, the same thing happens, right? So basically the primary job of the piece of the operating system that services your keyboard is to essentially retrieve information from the keyboard hardware and store it somewhere in the buffer. Whenever in some location in memory, whenever there is a chance that the operating system has time to notify a running program that, oh, by the way, there is information entered from the keyboard, it will do that. But as you're typing, it basically services it same thing over and over and over again, right? And only occasionally a program is notified that there's actually input, and then it begins to do things. So many of these little microscopic steps that take place, they constantly execute in a loop. It's just the repetition is probably just like just the most common thing that happens in the computer. All right, so same thing here. I'm talking about the reading mouse coordinates. So the running program also means that the program is already loaded into computer memory. Remember, I told you that I was, you know, we were talking about von Neumann architecture, which is pretty much the foundation of the architecture, the way computers are built. And part of that is that in order to execute the program, it has to be loaded in computer memory. So your program once compiled and built and ready to go, is stored in some kind of a file or combination of files on the permanent storage of some sort, your flash drive, your hard drive, whatever you use for your storage. But in order for the program to execute, a special component of your operating system called system loader will be actually loading your program into computer memory, organizing all that memory. And by the way, down here we have this picture of your program loaded in computer memory. This is very kind of nice picture. I copied it from John Loomis, a well-known educator. And so remember just a few minutes ago we had this slide where we had 0, 1, 2, 3, 4, 5. So 0 would be the low address. For some reason, in many books that talk about program organization, they kind of put low address at the bottom of the graphic. So here we would have like 0, 1, 2, 3, 4, 5 going this way, right? So your 4 gigabytes of memory will be in this area, and your location 0 or address 0 of that memory would be here in the low area, because it's like high and low, right? When you look at this from high and low perspective, you know, you want to put low towards the bottom of your screen and high towards, so this is a reversed sequence of numbers. But when your program is loaded in memory, that's the picture that usually exists during program execution. And today we have a chance to look at this. So let me stop this segment.